Okay, I will make a start. Kia ora koutou katoa. Welcome everyone. I hope everyone can hear us online. We've got about 30 people joining us online as well. My name is Megan Tuck and I'm from the New Zealand Coastal Society. And it's very exciting to have so many people here for our first regional event in Auckland this year. We're welcoming Patricio Catalán and Patricio Winckler, also joined by Sebastian Correa, who are coastal researchers from Chile. They're working on some climate projection work with OCEANUM. Patricio and Patricio will talk about tsunami hazard analysis and designing breakwaters and nature-based solutions to for waves of the future. We really want to thank OCEANUM and Becca for supporting this event. I hope people will grab some pizza and a glass or of wine or a beer or something to enjoy. And yeah, well, join me in welcoming Patricio for the first talk.
Yeah, okay, so in this presentation, I'm going to talk about waves of the future. That's the general name of the presentation. And together with Pato, yeah, my colleague, we're going to touch on several things which are kind of familiar to you. As there's skimmies, yeah. So I'm from the School of Ocean Engineering at Universidad del Paraíso. It's the only ocean engineering school in South America as an undergrad that offers this undergrad degree. And now, in this very visit, we are just doing our first trip abroad as PIs, Pato and me, of this center, which is a national funded center of basically disaster risk, resilience, and recovery. Yeah, it's called CIGIDEN. We hope to have the next 10 years working on risks. Yeah, this is a big bunch of people. Yeah, we are working on territories, society, hazards, infrastructure, yeah, and challenges. Those are the lines of the center. And since we came yesterday with Peter and Hannah, it's been very intense agenda. Yeah, so far we have visited the City Council or the Auckland Council, this place, also the University of Auckland, and so on. So it's been a real pleasure to meet all these people working in similar things to us. And so let's go to what we are here. So a little bit of context. So I have this, yeah. A little bit of just a comparison between the two countries. So, well, basically from this rough numbers, yeah, from northern tip of New Zealand to south, basically 1,500 kilometers, and Chile is 3 times longer. So we cover a wide range of climates, yeah, ocean climates, and also, well, so you can see that from the satellite in the north of Chile, we have the driest desert in the world. Yeah, and then in the south we have Patagonia, which is really cold lands, and in between we have a very open coast, and to the south we have fjords. Yeah, one of the longest strip of fjords worldwide, roughly like 2,000 kilometers of fjords. So if you're a coastal engineer in Chile, you have plenty of work. Yeah, several things to do. Yeah, so, and that's a good news. Yeah, and research-wise, I mean, there are lots of things to. So every single country probably has this saying that the country is like a natural lab for whatever you're studying. Well, it's also the same thing. Yeah, and specifically, oh, I'm going in the wrong direction. So specifically, so these are the type of topics that we are covering nowadays in Chile. Pato will go deep into tsunamis. We have earthquakes every once and then. 1960, May 22 was the largest earthquake ever recorded in human history. Huge one. We are also affected by sea level rise, but fortunately we are in a subduction zone. Yeah, we don't have such flat lands. Yeah, so it's kind of steep. Sea level rise is something, but it's not that relevant as other places in the world. And we do have coastal storms, yeah, like we are facing the Pacific Ocean and the westerlies, yeah, really strong winds generate super huge waves in the south, right? So I think that you have similar kind of problems. So this is basically what I'm going to talk about. This is a general framework of adaptation in coastal areas. There are lots of strategies to follow. Yeah, and some of them will be effective to some particular hazards, and some of them not. So I'm going to talk about kind of traditional gray infrastructure design, basically a retrofit of breakwater. Yeah, with new tools we've been developing. Then I'm going to dig into a nature-based solution experience we've been having lately near our near Valparaiso. And finally, if I have time, we will talk about the project we have with Peter and Luciano here, which is the Waves of the Future project. Now, yeah, let's go into this very first case. Yeah, this is called novel. Hopefully, you understand why it's novel once I finish explaining what you're gonna see. Okay. Yeah. So this is the setting. This is a breakwater located in Valparaiso. Yeah. Faces the Pacific Ocean. And this is just video. Yeah. This is our hometown. My office is somewhere here. In between the city. It's a very hilly city. So yeah, this is a video just drawn of the port itself. And the breakwater started being built in 1912. So this port was started being built in 1912. Yeah, and the breakwater took roughly like 20 years to be built. There was this large depression in between, the First World War, and so on. Several things happened, and this is one of the deepest breakwaters in the world, and it's being like affected, well, since early days by storms. You can see this the drone. It's not a drone. It's a video taken from the breakwater. You can see overtopping. Yeah, that's a huge distance. The breakwater, the crown of the breakwater is roughly like 10 meters above mean sea level. Yeah, and even though it's quite high, we have overtopping. And you can see that there is some displacement of elements of the breakwater. Yeah, since the breakwater was built along 20 years, there are at least three different sections. Yeah, because they, the contractors started building, and then some solutions didn't work, so they then shift the typology. So it's a very interesting facility. And the thing is that we have a concession system in Chile, and in 2030, the first concession ends. So they're going to be an international bid for companies to come there and operate the port for the next, say, 30 years. And if these companies come and look at this type of thing, yeah, it's kind of, what's the risk of putting the money there and invest in Chile while we could do something else elsewhere, right? So the breakwater is full of cracks, yeah, and displacements, and we've been working very hard to try to understand what's the current behavior of this breakwater. It was built, one of the sections, with blocks, which at that point were the largest blocks ever used in the world. It was a little bit less than 12,000 tons, and then they were built in the coast and then navigated. This is the kind of thing that it's currently is kind of normal. You go to the Mediterranean, you see all this type of caisson structures, but at that point was very challenging. So first thing we did was to try to find out the original plans, and we found them in a British library. Yeah, the company, Pearsons and Sons, that's the name of the company. It's not there anymore. Yeah, so we were able to contact a librarian there. Finally, she gave us this type of, this is just part of all the information they shared with us, because what we expected to do was to build a model of the breakwater. Yeah, there are some similarities with Kamaishi breakwater. So this is in Japan after the March 11th, 2011 earthquake and tsunami. This was a breakwater, but it was a breakwater built for tsunamis. Yeah, and it failed. It failed. It failed basically because of overtopping and seepage flows through the porous berm that supports the caissons. And this was found out by Taro Arikawa. It's a Japanese researcher whom we are working with. There's pretty close connection between Chile and Japan in terms of earthquakes and tsunamis. Yeah, we've been working 15 years, and well, way back before as well. So this is possible. It may happen. Yeah. And as I told you, in 1960 we haven't had an earthquake. So in order to complement the data we had, we conducted several surveys. So this is just a standard hydrographic survey, just trying to capture the bathymetry, but we also use LiDAR. We use also a multi-scan to have a really nice profile of the cross section, and we built this three-dimensional model. Yeah, which I mean, you let it stay there for a while, and you're gonna see the cracks. You're gonna see whatever you find in the surface of the structure. We've been conducting also depth measurements. Yeah, so we're just about to have a good model of the breakwaters. Yeah, so together with Pato and some students. Well, Pancho Saez. He's not a student anymore. He's also part of CIHIDEM. We have conducted a probabilistic tsunami hazard analysis. So they have run 6,500 cases to calculate, for example, surface elevations, velocities, yeah, and eventually loads acting on the structure. So one of the things we found out is that the conventional design methods like the ASCC or the Japanese standard, they are very basic when defining the loads of tsunami loads, just like hydrostatic pressure, nothing else but that. But there is also, I mean, you have a tsunami, you also have velocity, so momentum is strong. So you need to capture also velocities and transient effects, and those are not in the guidelines. So what we did was to, define several sections of the breakwater, and around this, let's say, run this 6,500 models and capture the variability of forces of these three components, like the standard one, the hydrostatic one, but also momentum and transient effects. Yeah, and with that, which is like the loading of the structure, we went a little bit more deep into the structure itself. So this is a finite element model that captures hydrodynamics and also porous flow through the berm, and also the motion of the caisson, which is it's modeled as a monolithic element. Yeah. And with this kind of model, we have been doing several things. One of them is this is just like this is just hydrodynamic model. Yeah, but then I don't think I included the one that moves the caisson. Oh well, so that was a kind of failure of the bearing capacity. At the end, you see like well, basically sink the caisson sink in the structure, and this was basically because of seepage flow. So seepage flow promotes the loss of bearing capacity and eventually can trigger the overturning of the caisson. Yeah, that's a kind of failure mode that wasn't reported in literature before, and there are some physical tests which I didn't include here. Yeah, but then, it's something that it's kind of a new failure mode, which sum up to existing ones, like the original one, sliding, overturning, and yeah, that's it. So with these tools, what we've been doing is to try to understand how the porous flow works, yeah, how the overtopping works, and which is responsible of the failure mode, right? And we can these are experiments conducted by Taro Arikawa in Japan, and you can see that this failure mode, well, the video just slide to the right, but there is, the video in the right shows how the seepage flow eventually start moving part of the material of the berm. Eventually, the berm, overturns. Yeah. So this is something that we've been working on. So usually, when you have structures, you use fragility curves. Yeah, and in this kind of representation, you can have some kind of, it's a kind of tree of failure modes. Yeah, which depend on the velocity and also the free surface elevation. So depending on that combination of variables, flow velocity and free surface elevation that you can capture from, for example, shallow water equations or similar, you can actually understand how the structure will fail. So this is specific for this facility, for this breakwater, but we think that showing results in such a way could eventually inform designers to improve their designs beyond what's requested in the norms, right? Okay, that's traditional. This is completely in the other end of the spectrum, which is working in an engineered kelp field. So I've been listening to all these conversations yesterday and today, and coastal erosion is an issue here. In the morning, we were at the University of Auckland talking about things. We also have kind of a similar problem. Yeah, in Chile, we have conducted a couple of surveys, and roughly like 80% of the beaches are experiencing coastal erosion. Yeah. So, this is not working. Well, it's going absolutely the other direction. Let's see. Yeah. This video supposed to be a video. Yeah, shows like a natural kelp field. Yeah, and so I think we all know that if you have, it's not working. Anyway, the video show how waves are being attenuated because when they go through the kelp forest, and so it's because of transformation of wave mechanical energy of the waves into motion, and also turbulence, and also this forests, they promote reduction in speed and deposition of sediments. So they play around. Well, also they capture CO2. Yeah, so they're pretty like interesting and attractive to try to control coastal erosion. Yeah. So yeah, we've been playing around with all these techniques just to diagnose the patient. So yeah, it's a very dynamic system. But overall, we know that erosion is something relevant, and probably in the future it's going to be even worse. Yeah, because of sea level rise. We were just saying that in the morning, is that in Chile we cannot decouple climate change from earthquake generated changes in the position of the seafloor. And I was saying that in 1960 there was an uplift of 5.2 meters in one single island because of the earthquake, and a subsidence of roughly a little bit less than 2 meters along 1,000 kilometers of coastline, which is a little bit less than the whole New Zealand. Yeah, imagine that. So it's important. It's important. So we've been looking at this type of specific species, which is called Macrocystis pyrifera. It's a giant kelp, and it has pneumatocysts, which are kind of small balloons. You can see it, they give them like a positive buoyancy. So Darwin, when he went to Chile, 1835, he wrote that he had found some of these species even at 70-meter long individuals. Yeah, so it's not that they go down to 70 meters. It can be like 30 meters, but then they start, merging in the surface, and they form some sort of network. Yeah, and yeah, we have seen that this is a potential solution, nature-based solution to aid traditional structures like breakwaters and that kind of stuff. By themselves, probably they won't make it, but they can aid to reduce, for example, loads and structures, and reduce the crown of the coastal defenses and so on. So we've been doing several things. One of these is playing around in our lab, and you can see it's just very simple models. There's a sack there. So everyone is called Pato there, except Christian Flores, this guy over there. That guy he used to be a former student of mine. Yeah, we're all the time playing in the lab. Yeah, but what we've seen is that on a prototype scale, model of a prototype, we have already deployed near our. So we also been characterizing the individuals. So, for example, this is a former student also working in the south of Chile, and he has been collecting individuals, taking pictures of them, making analysis, capturing the geometrical properties, and also the hydrodynamic properties of this kelp under currents, only currents. We have done a little bit of waves as well, but it's very hard to deal with this individuals when you go and try to deploy an engineered kelp field from zero. And I will show you one of the reasons why we have faced, basically. So this is the prototype we designed a couple of years ago. So it's a net, it's a flexible net, and it has some reefs that give weight. So it's in the seafloor. And then in these lines, what we do is to plant seedlings like individuals, and they grow really fast. So when we started the project, we thought that even in less than 1 year, we would have a whole kelp field working like properly. It didn't work, for several reasons. But anyway, regardless of that, this is an interesting way of actually harvesting kelps if it doesn't work for the purpose we're looking for, which is reduction of wave energy. In this particular project, we've been working with local fishermen because they know lots of stuff we don't know. And we have also tried several ways to put the seedlings. One of them is hand one by one. The other one is just put the line, then let the seeds, attach into the line and grow by themselves. But that takes a little bit more time. So in this particular device, we were aiming to plant 27,000 individuals. We ended up doing a little bit less than 50% of that. Because it's very dependent also on the season. On the several variables defining the quality of the water. So these are the first attempts we did. So you can see the main lines. These are the thick ones are the main lines, so the thinner ones are the seedling lines. And you see all these seedlings that actually grew quite fast. It was very hard to build it. And then what we did was to put some buoys and train an AI to capture the wave height before and after. It was calibrated with pressure gauges. And so, actually, it went pretty well. So we monitored the behavior of the kelp, but they never made it to the surface as we were expecting. So that's but part of the story. But okay. So why this happened? So everything is connected. By the end of the first year of the project, there was this large storm. We published a paper of this storm, which was, according to all the data set we analyzed, was the largest storm ever occurring, recorded and modeled in the North Pacific. So this is the North Pacific, and the fetch was roughly like 1,000 kilometers and winds of 120, 110 kilometers per hour blowing constantly there. So near the source, the wave heights were a bit higher than 20 meters. And because of wave dispersion, all these waves arrived into Chile in the New Year's Day. So it was fantastic because in Valparaiso Bay, we have several places where we, throw fireworks, and all these barges were, swaying away. Fantastic. But the waves reached, so coastal engineers prepared 25 seconds, peak period, and wave heights of 3 meters. So how do you deal with the drag forces? It's almost impossible. So that was the end of the story, because all the the kelps ended up in the beach. So extreme events are absolutely have to be included in the design. There was also some biological issues. So there was a kind of what is it, a mind blower, and now we're still rethinking on how we could keep going with this project. We really think there's an opportunity, probably not in so exposed sites. Probably you're going to have to find out places within bays that the waves are a little bit milder, or go to the fjords. Yeah, that would be another option. Yeah. So, and this is a picture when we deployed the first, so you can see the reefs there on top of the barge. It was pretty fantastic. Yeah. So that's the second part of the story. Yeah. Like nature-based solution, they need lots of space, they need lots of experience, luck, and good design, which we didn't achieve. Yeah. And third part of the story, yeah, is the project why we're here, right? And it's called Waves of the Future, but it's not only waves. It has basically three elements within it. So these are the researchers. So that's Pato with her. Yeah, not anymore. And so the project has first the development of a database, and the database has 6 variables, which is winds, atmospheric pressure, waves, storm surge, tide, and sea level. Yeah, the basic idea is to make this data readily available for designers. Yeah, to make it easy to work. Yeah, this is funded by the state, so it's a $200,000 project, 2 years. Yeah, very practical. We aspire to keep working with this type of data and do research and pose questions once we finish the work we're doing here, right? Which is upload this basis to OCEANUM and so on. But we're also doing this is Spanish, but the objective 2 is basically developing a guideline for design of coastal structures considering climate change. Yeah, not only just like include sea level rise, you could do much more interesting things. And so we also think that this guideline should be absolutely linked with the data itself. So you guide the consultant, and you say you should try, if you want, this type of steps. If this is a small, let's say, for example, coastal defense, if you go to a port, for example, probably the calculations have to be more refined, and you can use this data in such a way. So we had to think of how we're going to make it to make it handy for practitioners. And the third one, which is something that we've heard a lot since we came yesterday, is to develop a guideline to calculate hazard maps, flooding hazard map, coastal flooding hazard maps along the country, because it's mandatory nowadays because of a law enacted a couple of years ago. So one of the things that we have here, and so these are my kids, they are, well, much older now, is that we do have sea level rise, and this is kind of a similar plot that you can see elsewhere in the world. Yeah, so within the lifespan of a structure, remember the breakwater was started building in 1912. Yeah, now it's already how many years? 114 years old. Yeah, so you have to think ahead. And well, so projections say that we're going to have, well, at least 0.5 meters more of water level. And we have been playing around with the projections. Yeah, so you can see here this typical short-term forecast from which you get the wave climate and also the changes. So we're pretty much interested in the changes, like future changes. That's in the right-hand panel is changes for the end of the century. Yeah, but we are using also an intermediate term horizon, right? So this is the type of thing we are doing now. So we also had a conversation in the morning in the University of Auckland about what's the response of beaches with waves, and so these are simple wave roses, like historical one, and changes expected for the future. We've seen so far that the waves are coming more from the south because of all the migration of the westerlies to the south. Yeah, and so the waves are coming more from the south in Chile, and with longer periods because they come from like larger distances and a little bit smaller heights. Yeah, if you were interested, for example, in overtopping of structures, yeah, so if the height is reduced, then the overtopping is reduced. But if you have a longer period, there's going to be a more overtopping. And if you sum up the sea level rise, then probably it's going to be a worst condition. And now, if you look at the direction, it will depend on which side are you analyzing. If you have a bay, probably things will behave differently in the north part and the south part of the bay. So you have to look in detail. And so these are very general calculations we've been doing so far. Yeah. So since the country is so long, we have places in which the winds are going to increase in magnitude. In some places, it's going to be reduced in front of a country. Offshore the country, and the waves is also similar. Towards the south, waves are going to increase, yeah, but in middle latitudes they are going to decrease, yeah. So this is not that useful unless you take this information into a coastline. So we are working, so especially Sebastian is working in downscaling this data to several points. So these are some of the bays or areas of interest we have along the country. Yeah, so we have 124 nodes where we are computing all those data sets, like these 6 variables. And from that information, we can, for example, calculate downtime of burst sites for whatever type of vessel we have. Because that's a kind of what is it outcome we aspire to do once we finish the project. Just jumping from the database and the guidelines to calculate impacts, and the impacts can be either operational or structural, right? And we've also Sebastian has been working also in short-term forecast, 7 days. Yeah, we were discussing today in the council with Megan. Yeah, we have already what is a forecast model which includes waves and also tides, so you can calculate like very broadly things like overtopping or run up in some places. So it's like overall we have done so far hindcast like 35 years, a little bit more. Yeah, we're running the short-term forecast, and now we're going into like long-term projections, right? So that's a whole picture. And so we've been calculating this. Will be very hard to calculate, but these are just very preliminary calculations of run up within a bay. Yeah, so it's you can we're basically analyzing the whole country with offshore nodes and then going to specific places, and you see that within a bay changes in, for example, run up can be very relevant, right? So I think I'm coming to the end of the presentation. I will hand this to Patricio Catalán, the Tsunami guy. Look at his shirt. Questions first? Huh? Okay. I'm not sure, Mega, you're one.
Up to you. We can do questions now, or if you want to do them combined afterwards, whatever.
Up to people.
Should we do some questions now? If anyone has any questions in the room, should we start first?
I just have a very quick question. It's like, what happened when those giant kelps like passed away and got to the beach? What about like the natural ones that were also growing maybe in the rocks, like the natural reefs? They also were affected by the big northwest swell.
Interesting. The people online, the question was what happened to the natural kelp, the ones that weren't put out there, but the ones that were already there in the storm.
This is my very friend Gert. We know each other from Chile like 40 years ago. Yeah, the thing is that so there are different species. Some of them are they don't grow up. So we put the scalps that had the ability to go to the surface, and those were washed away. But the natural ones, which are now the species, they didn't. Well, the only species we found in the beach were the ones we planted. So it can be either from the site that we planted or somewhere else. But these are local species. That was one of the requirements from the beginning. We didn't want to introduce any new species to avoid any kind of ecological disturbance. Yeah, but yeah, that's it. We're also discussing the idea of doing ensembles of species, like some of them like in the bottom, so they improve like friction, and some of them like reaching the surface. But then that's this was a 2 years project, $200,000, and ship barges and all that stuff. The funding wasn't enough. But yeah, it was a prepared question. Anybody else?
I was wondering whether the findings.
Oh, that'd be great.
I was wondering whether the findings from the Valparaiso breakwater analysis would eventually find their way into the Japanese design code and perhaps the ASTE design code.
Well, I think that changing a code takes time. Yeah, but the Japanese code has changed 3 times in the last 20 years, maybe something like that. So probably, well, one of the good things is that Taro Arikawa, which is a kind of respected coastal engineer in Japan, is in the project. He's working with us, working together, and we're going to go probably if we are able to do it, conduct experimentally in his lab this present year, and like testing other conditions that we have found out like interesting, but then it will take time. And I'm not sure. Pato is more close to the US group that built this kind of stuff. So I think that we will first inform the scientific community about these findings, and see if we can push. At least on a local scale, on Chile, we aspire to include this type of approaches in the guidelines, even though this one is for tsunami. The whole picture of having these trees of failure modes, which is something that's, it's not like, wow, space science. No, it's just thinking instead of, putting a load and it just overtops or so it overturns, a little bit more complex. Probably the limitation is that the numerical model we're using is probably a bit advanced for conventional consulting because it takes time. It took us 2 years to build the model and make it operational. So yeah, I mean, it's kind of a trade-off. Yeah, really good question. Yeah. Pato?
Okay.
Thank you very much.
Thank you, everybody, for the opportunity. Thank you, Becca, for hosting us today. Thank you for the New Zealand Coastal Society for also hosting us today and the opportunity to discuss a few things with you. And thank you all for making Pato wear a shirt. It's the first time in 30 years that I know him that I've seen him wear a shirt. So it's quite an event. You don't really know what happened. Okay, I know my presentation was entitled something about probabilities of tsunamis, but long story short, I made a mistake. I did it in all my runs a couple of weeks ago, so I said, oops. But I'm going to share something that is on a different wavelength, but it might interest you because we have been analyzing tsunami resonance through observations. And we learned quite a bit of that. It has been a topic that has interested me for a long time. So,
¿Tiene el pasa?
I'm somewhere.
They're in the table.
Thank you. Okay, so yes, I guess you know that we're just one really long swim away from each other, but that means that even though the water is cold, we can communicate fairly well. But I guess the long-term effect is that many of the processes that affect us here in New Zealand and in Chile probably are closely interlinked. We were discussing earlier this morning PDO, SAM, and El Niño oscillations that are affecting the Pacific Ocean as a whole, and tsunamis are no exception. Just a little bit of history. This is basically the historical record of tsunamis in Chile. What you see here is the lines basically depict the rupture zone. You know, the earthquakes are not just a single point. They cover a relatively long stretch of the subduction interface between the two plates. And the reason why we have such large events as the 1960 is that we can have ruptures that can span more than 1,000 kilometers long. If we go back in time, you can see that even though our record is basically written record, it covers the whole country. There's nowhere you can escape from this. And also we have some really large events in the past that point towards a recurrence rate, right? So earthquakes happen every so often. In Chile, we have at least magnitude 8 or so on average every 10 or 15 years, which is quite big. And so in northern Chile, southern Chile, so the whole country has been really exposed. But it was very surprising to us in the aftermath of the 2010 event, which was magnitude 8.8. That even though as society we know a lot how to react to earthquakes ourselves, I mean, you can run, it's shaking everywhere. That's the basic something we learned from the beginning. We didn't have a lot of memory when it comes to tsunamis, even though we had the 1960. And the reason for that is that basically there was a sort of lull, a period of 50 years without significant earthquakes. And that meant that the memory, communal memory, and it was a very distant event. And it became more an anecdote than anything else. We had earthquakes in the interim, but they didn't create a large tsunami. So that was somewhat surprising. This is the 1960 event, some of the data. Pato has been very active in trying to reanalyze all the data. And you can see that even here in New Zealand, in the northern end, we had some large runout. But that event affected the whole tsunami, I mean, the Pacific Basin. So it's basically the Pacific Ocean is just a small pond for our earthquakes. When it comes to directivity, I like to make the analogy that this is like a flashlight that you can point in one direction. So most of our directivities are geared towards Japan. So we have this long relationship with Japan. We send a tsunami that way, and they send another one our way, and then so we're always fighting. So this is the main theme of directivity, and this is the work of a student that just finished, an undergrad student. So I asked him, okay, how we can make tsunamis to go to Newcastle and Port Denison, and eventually you can, okay. But this is just a side beam, okay. So it's not the main energy; it's a little bit of energy that goes to the sides, and eventually, well, bad news for you, we can hit you. So don't get mad and don't send anything to our like Japan does. Okay, please. Anyway, so in analyzing all this information, we have been very active in trying to understand and model tsunamis. So we're basically, I like to think tsunamis as any other wave, that they have a lifespan. So we have a source, that is the earthquake itself. What you are seeing there in red and blue is where you have uplift and subsidence due to the crust deformation. And that's basically what gives energy to the water column. And once you transfer that energy to the water column, it just becomes like a stone thrown in a pond, and waves will propagate away. And I think most of the time we care about what is going to be the effect inland. So that's the inundation phase. And what is interesting here in this plot is that you can see a city in northern Chile. The colors depict the flow depth, okay? And 4 different dots are 4 different locations in the same city for the same event, synthetic event. Doesn't really matter which one is that. But you can see that we have very distinct behaviors. The upper panel shows a wave that hits 4 or 5 times, distinct waves. So that has been something that we have to basically relearn, in the sense that tsunamis are not just one wave. In another one, we have an initial peak and then a slow decay, but always that's our low-lying area, so we get inundated continuously. Whereas in this other region, in the bottom graph, you can see that it's just a short spike. And same events, same city, completely different behavior. So analyzing the tsunamis requires a lot of specific details, and that's the reason why we have been trying to carry out lots and lots of simulations, especially for complex behavior when you're just in front of the source area. This is a collection of different tsunamis recorded at the same city. I think this is in northern Chile, in Arica. I don't know if you can say fortunately when we talk about tsunamis, but since Pato was saying before that we are a natural lab, at this particular place, you can see that we have close to, this one is 12 different events, different magnitudes coming from different places. And usually in time, I've been, oh, sorry, something should have happened and it did happen. When we look at the time evolution and we remove the tides, we can see in general that we will have a few waves at the beginning. Usually we'll expect a very strong decay of the tsunami energy or the wave fights. That is that cartoon over there. But you can see that we can have some late arriving waves that can be larger than the first wave arriving. And what is interesting in this case that you can see later on, even though the energy decreases fairly rapidly, we can sort of having ringing. So that means that the waves down and go up in terms of energy. And that is a big problem because usually when we think about acting or responding to a tsunami, we tend to care about evacuation, right? So to prompt evacuation very quickly for people to leave the potentially affected areas. But then the question is, when is it safe to come back? That in many of the tsunami warning systems, they don't have a clear guideline for that. And the question is, how do we can better understand the long-term behavior of the waves in order to make people to come back safely? In Chile, our rule is to, after the event begins, you will move away from modeling towards observation. And that means looking at this data. And if you have 3 consecutive waves below the threshold of 30 centimeters, you can call them the warning. But then at places like this, you may have 3, and then it will pick up again. So is it safe, and how can we forecast that? So that's basically what guides what we began to understand, or we attempt to understand, because we are thinking about when we can do safe evacuations. Probably unlike here, and part of the reason of driving this is that we have had several evacuations with smaller events. So we don't only need the large events to trigger a tsunami that is going to be destructive. For us, the problem is the gray ones, the small earthquakes that can trigger a tsunami that is going to be recorded, but then eventually we need to evacuate, and then you get the Peter and the Wolf effect, because, oh, they told me that I need to evacuate and nothing really happened. Well, it did happen. The problem is that it didn't go steady. So public perception here is significant. Well, nothing new here, in fact, because if you go back to an article from Onda et al. In 1908, you can see that this sort of behavior was already recorded. They did cover the entire island of Japan, looking at specific bays, and they were able to see that bays with narrow openings do not show significant resonant oscillations. They don't call it resonance in that article, but I did a little bit of a translation. The most significant resonant amplification occurs in elongated waves, long, narrow bays. Sometimes, and this is interesting, contiguous bays or those open coasts can show similar resonant periods. So if there are 2, perhaps they can behave as 1. In some bays, resonant periods are constant, whereas in others, they change but are constrained within a range. So that means for different events, the bay behaves always the same. In others, it changes. So that's the first clue, because how we can distinguish between those bays. Well, longest periods, the Merriam formula, and storms and other phenomena can also induce oscillation of similar periods. So 1908. Okay, so I don't know. the first time I found this paper, it was, everything is solved already. In fact, it wasn't, okay? Why the interest in Chile is because when you have resonance, you can also have problems in terms of how you to deal with the emergency. This graph here shows the actual measurements, the numbers there, different tide gauges along the coast for the Maude, the 2010 event, and another one in 2014, 8.3 and 8.9. So you can see the red colors are areas that exceed the threshold for 1 meter. That's an alarm. And the orange ones are the ones that exceed the threshold for 30 centimeters. And you can see that even though the star depicts the epicenter, it's not really relevant, but just to give you a clue where the earthquake happened, you can see that there is a strong decay in terms of the amplitude, but then Arica goes up. So we have in the city of Iquique 60 centimeters and Arica 1 meter 20. How do you explain the population? I mean, people, not the population, people that you need to evacuate Arica, but not the people that is further downstream. Okay, that's a big problem in terms of emergency management. So something funny happens there. And if we look at the one from Ijapel, you can also see that even people in cities further south, they don't exceed the minimum threshold of 30 centimeters, yet Arica again. Okay, so we have something going on there. So it complicates emergency communication, and we need to understand. So we have that on hand. We also have late arriving waves, and we want to deal with time in the sense of how long it will take for the amplitudes to decay enough for people to come back safe. The only equation, I think. So the methods are fairly standard in the sense that instead of working in time, we're going to do a Fourier transform and analyze the tsunami records in the frequency domain. And the idea is that you're going to have a source term, which is here, that orange, this Z of F, that relates to the energy content at the moment where you trigger. Okay. And then that is going to be just linearly transformed, amplified in frequency by all sorts of processes like refraction, reflection, modulations, and other transforms. And you may have some other amplifications, but usually they're not relevant. The key point here is that now you have two competing or leading order phenomena. One is what is the characteristic of the source, so the tsunami itself at the moment it's generated, and what are the characteristics of the pathway of the tsunami between the source and your point of interest. And the question is which one dominates, or in other words, what do we need to know in advance? Do we need to know the bathymetry really well, or we need to focus our effort in understanding the source, or both? What if we can understand one of them better, or which one dominates, perhaps can help in the long run. So a very weak analogy, I tend to think like bathymetry or all these complex systems as a system of drums. So we have a collection of different modes of vibration, okay? But you know that the drum set doesn't do anything unless there is a drummer, okay? So which one dominates when you want to play music? Are you constrained by your drum set? Or it depends on your ability as a drummer? So let's think of the drummer as a tsunami and the drum set as bathymetry, okay? And which one is more relevant for the music you want to hear, okay? So standard methods, we rely on tide gauge records. The benefit is that we're going to use the actual data from all these events, but the problem is that we have few events. And the real problem is that they are going to be conditioned by the location of the tide gauge. I heard that Peter has been working a lot on port resonance, and sometimes it will like to put several sensors within a port in order to characterize the whole response of the port. With tie gauges, usually we have, right? We're constrained for that. And this is a sort of giveaway plot because this is the records at Antofagasta, that is period on the x-axis. This is normalized amplitude. And you can see that Antofagasta, regardless of the event, it always resonates at 40 minutes. Okay, so okay, there's one place that the tsunamis are always behaving in the same. We coupled that information with a free oscillation model. So since we can treat the ocean as a membrane, we can use numerical methods to try to characterize the eigenvalues of deformation or amplification. And you can see this is Antofagasta itself, the same city where the previous plots were I showed. And you can see that the first mode, look at that number, 44 minutes, spot on with what we saw on the records. And you can see that Antofagasta, the tie gauge is actually located on the sort of the side of the main lobe of amplification. The second mode for the complex system is at 23 minutes. If I go back, 23 minutes is right here. Okay, again, spot on. But the third mode is at 17 minutes, and it's actually where close to 1 hour. So we don't have information there. And then so on and so forth. So Antofagasta is well placed, if you want. Could have been much worse if that city was built up there. Okay. So if you can follow me, basically that is the area where maximum amplification can occur, and Antofagasta is okay, in a good position. So we have been working on this for a while, and now the question was, can we classify bays in advance based on all this data? And so only a handful of studies on resonance have been using several tsunamis. So Wang et al. Used 4 in Japan tele-tsunamis coming from Chile and other places. And they found that, or they proposed a classification based on 3 categories, consistent with Honda. Consistent response among tsunamis, so the bay always behaves the same, mixed response, and high variation among them. So this is what we use. 30 years of tsunami records, up to 18 tsunamis of different origin, 2 method tsunamis generated locally, Tonga event, so 1 volcanic tsunami, 13 tsunamis, 8 coming from Chile and 5 coming from other places, and 19 locations along the coast. More music for you. Okay, that is actually, for a while I thought that was a spectra, and it's not, it's a time series. Anyway, we can discuss that later. So again, now that we have the record, we can also analyze the background. So in the absence of tsunamis, you can see how the bay likes to move. Okay, so that is called the background spectrum. So basically, you look at the tide record, remove all instances where you have a lot of energy, and just look how the bay likes to move. So and you can see that Arica is kind of noisy, different peaks spread out over a wide range of frequencies, whereas Antofagasta, the one that I showed you before, again, those 2 peaks, very, very big one. And so how do we put together the information of all tsunamis? This is again, all tsunamis at a site, linear scale on the y-axis, logarithmic scale on the x-axis. The R stands out for regional, teleseismic, and some near field as well. And we decided to do something very simple. We took the average. Okay. So when we take the average, we have a sort of a spectral response of the site itself. And you can see the shaded area that is the standard deviation. And those points are places where we have signals to noise ratio that is very large. So the mean compared to the standard deviation. And then we compare that with the background in the absence of any significant energy in the system. And we began just eyeballing, to be honest, at first, the different locations. This is a summary. So in areas where we have the background significant and are the dots, and we analyze every single site, comparing the two, and we came with a proposal. So we found that if similar to Wang, we can have certain bays where there is a clear modal response regardless of the tsunami. Remember, the shaded areas correspond to the average about among several events. So places like Mejillones or Antofagasta or Coquimbo or Quintero, they're dominated by the bathymetry. So regardless of the characteristics of the tsunami, those bays will like to move always at the same rhythm. It's like they have the preferred tone. So whatever the tsunami, wherever it happens, it always oscillates at the same rhythm. There are some other locations, we classify all 19 of them, where you can have a wide range of periods concentrated on a band. And there is some variability among events. So that is the case of Arica. So Arica likes to move as a certain response, but sometimes the tsunami itself carries a little bit of signature. So that is, those are places where you cannot predict well in advance what is going to happen because the tsunami carries a little bit of weight. And of course, there are places where all bets are off. The drummer is the one carrying all the signal, but bathymetry doesn't really control the signal. Okay, so small drum set, big drum set. Some places it matters, some other places it doesn't. When we then want to compare with analytical solutions. So, for ports, you can have Miriam formula, and depending on the chord length and the mean water depth and responses. And we found that in analyzing this, usually what you care is about the planform geometry. So what is shaded here in brown. So basically you look at the shape of the bay or the port in planform and how well defined it is, so that gives you an idea of which kind of these solutions you can use. And also you just use a representative depth. It can be the offshore edge or an average depth. Depends on which one you want to use. So we found that a good correlation of places where the bathymetry was easy to understand. So for instance, when I explained you about Arica, this is located in northern Chile. So this is the southern shelf of Peru. There is a kink in the coastline of South America. So Chile is straight up and Peru goes a little bit off towards the west. You can see that most of the first mode, the famous first mode of Arica, is controlled by what is happening on the shelf of Peru. But the second mode, you can create, you have a sort of standing pattern. And the third mode, it depends on both the northern end of Chile and the southern end of Peru. Okay, so the shelf dominates what's happening in Arica. And eventually you can have a little bit of input from the tsunami itself. Antofagasta, the one that we analyzed before, the first mode is very well defined, and so is the second and the third. So that bay is very well defined in plan form. So it's almost textbook, and is fully controlled by the geometry of the bay. But, and this was the interesting part, We live in Valparaiso. Pato showed you the breakwater that is located right where that dot is. And in Valparaiso, we have this sort of weird situation where we had many tsunamis in the past, but most people used to believe that there are no tsunamis in Valparaiso. So everything just passed outside the bay, and we never got significant inundation. And there was this sort of urban myth that there were no tsunamis in Valparaiso at all. Of course, coastal scientists you are, coastal engineers, you know the tsunamis are there. The problem is that we don't see them, right? And the reason I struggle a little bit to understand why that happened. And people were saying, oh, the bay is too deep. Okay. But you know that 50 meters is nothing for tsunamis. I mean, tsunamis are such a long wave that 50 meters, they just hammer through. Well, the thing is that we have another bay a little bit further north. Well, we have another one there, but that is far enough to be independent. But you can see that here in the Bay of Concon, which is further north, we get strong amplification. And usually, and this is where the comparisons begin, we get coastal inundation due to tsunamis in Concon. So of course, if you think of in terms of a layman person, they will think, oh, Concon gets a tsunami, but we don't, because there is inundation there, but nothing here. And why? And you can see that here we have a strong amplification. So these two bays that when you look them in plan form, they seem to be fairly independent. They are not. They act as a system, like one of those systems that Onda et al. Said, sometimes you have bays that are sort of coupled with each other. So planform geometry is not enough. What else do we need to put into the equation? So you can see those lines there, and we began analyzing just the depth profile along those transects. And we found that most of the category 1 bays are characterized by, I'm going to go back a little bit. So if we think in terms of Valparaiso Bay, we're going to have a southern profile, a northern profile, and a central profile. Okay, so for each bay, we use 3 profiles to characterize them. And the 2 end profiles are showing in the shaded area. And the central profile is shown as an independent line. So for most of the bays where there is significant control, what you need to have is a very steep headland and then a shallower middle section of the bay. So basically the headlands are the ones that are separating that bay from the other one. When you have comparable slopes between the headlands and the chord profile or the center profile, those are very good for energy trapping, and they act as a single system. So there is no distinction between the two, and that generates edge waves that are propagated along the shells. Okay, so they can cover the entire system, and then the actual source becomes relevant because the edge waves are going to respond to the tsunami itself. And when we have headland and chord profiles but are comparable but steep, all the time. So I guess that was the main takeaway from our legal analysis, the fact that we need to consider what is the shape of the headland profile. So what happened here, going back to Valparaiso, is you can see that that headland is actually super steep. And that headland up north of Concon is also super steep. But this one in between is fairly shallow. So the tsunami see the whole system as a just and we get pumping between the two. So it grows in one and it sort of forces the other one. But then the maximum amplification happens in Concon, and that explains in part that in Valparaiso nothing happened. Okay. But that's not all. Okay. So once we did the analysis, we thought, okay, what if we can actually provide a little guidance in terms of quantify the response, and we were not as successful. We tried to find the correlation here between the mean spectra. Remember, I took the average and the background spectra, and we get some relatively good results. Reds are the ones that are category 1, and blue and green category 2 and 3, but it's not super hot, so I wouldn't bet on that yet. And going back to Arica, so what is the real problem for us? Because if you, I showed you those maps, but that is where Arica is. And the real problem for us, in Chile at least, is that most of our cities are built on the southern end of the base because they are protected from the winter swells and the strong waves coming from the south. But it turns out those are the worst locations in general for tsunami, because that's where we get maximum amplification due to this. And we have seen that in the past for several tsunami events. Actually, the cities are at the wrong location. So what do we do now? Okay, and that's it. Okay, thank you so much for the opportunity. And again, and for having Patricio, for example. Thank you.
I think that's it from us, but thank you very much for coming. I think there's still a bit of pizza left. So you're more than welcome to grab some before you head home. I don't know what time we have to be out of here. Is it 8? Okay, so there's a little bit of time for networking and chatting. Thank you very much.